So today we will discuss the potential functions of module 1 of the electrodynamics course. So we know that the divergence of the magnetic field is 0. The quantity whose divergence is 0 is generally called a solenoidal vector. So there is a vector over here and its divergence is 0. So B is called solenoidal. So you have studied in the mathematics course that every solenoidal vector can be represented as a curl of another vector. So B can be represented as del cross A. So since the divergence of a curl is always 0. So the magnetic field intensity vector can be represented as a curl of a vector A. So the vector A here is called the vector potential. Vector potential. So, and in electrostatics, we have seen that del cross E equal to 0. The curl of the electrostatic field is equal to 0. So, if this is an irrotational vector, a vector whose curl is 0 is called an irrotational vector. So, an irrotational vector can be represented as a gradient of a scalar. So, therefore, we can write E is equal to a gradient of a scalar minus V. So, E is negative gradient of V, where V is called the scalar potential. But this equation is not true for the dynamic or time varying case. For time varying case, we know that del cross E is not equal to 0. It is minus dou B by dou T. Minus time rate of change of magnetic field. So, del cross E can be written as, so substituting B in terms of A. So we have already seen that the magnetic field is del cross vector potential. So del cross A over here. So del is an operator with respect to position. Dou by dou x, and this is a time operator. And these are interchangeable. And therefore we can write this is minus of del cross dou A by dou T. So we can interchange this and RHS towards left, we will get del cross E plus del cross dou A by dou T is equal to 0. So del cross of E plus dou A by dou T equal to 0. So curl of E is not equal to 0 in the dynamic case, but the curl of E plus dou A by dou T equal to 0. So in dynamic case, E plus dou A by dou T can be written as the negative gradient of scalar potential. The static dou A by dou T term 0 equal to minus gradient. So this is applicable for both static and dynamic case, and therefore we can write E is equal to minus gradient of potential minus dou A by dou T. So this is the expression for E in terms of scalar and vector potential. So these are the expressions for electric and magnetic field in terms of the corresponding potentials. So this is also called the potential formulation in electrodynamics. The potential formulation advantage എന്ന് പറയുന്നത് നമുക്കറിയാം electric field magnetic field vectors ആണ്. So we have to specify 6 components. E has got 3 components, Ex, Ey, Ez, and B has got 3 components. So total 6. But if we use the potential formulation, so V is a scalar which has got only one component, and A is a vector which has got three components. So a total of 4 components is only needed in potential formulation to get the electric and magnetic fields. So once the scalar and vector potentials are known, we can easily calculate the corresponding fields as B equal to del cross A and E is equal to minus del V minus dou A by dou T. So in field formulation, we require 6 components to represent electric and magnetic field, while in the potential formulation, we require only 4 components to specify the electric and magnetic field. So, 3 components of A and 1 component of the scalar potential V are required to specify the electric and magnetic fields in the potential formulation. So, the electric field intensity depends on both the scalar potential and the vector potential. So, in the static case, the electric field intensity depends only on the scalar potential. This term will be 0. So, we can say that an electric field intensity arises from the accumulation of the charge through this term and from the time varying magnetic field through minus dou A by dou T term. Minus del V. So, charges accumulating potential and electric field. So, if there is a time varying magnetic field, there will be electric field intensity. So, we can say that here B depends on A and E depends on both V and A. So, the electric and magnetic fields are coupled. So, in the static case, they are decoupled because electric field intensity depends only on the scalar potential and the magnetic field intensity depends only on the vector potential. But in the time varying case, they are coupled. Both the electric and magnetic field intensities depends on the vector potential. So, here the first term in the electric field intensity is negative gradient of potential is due to the charge distribution. And charge distribution rho, and second part minus dou A by dou T is due to the time varying current density J. So there are 2 sources for electric field, time varying current density J. But in electrostatics, the source of the electric field intensity vector is rho alone, while in the dynamic case, the electric field intensity has got 2 sources. One is the charge distribution and another is the current distribution with current density J, which is time varying also. But J dayum V dayum expressions are already പഠിച്ചിട്ടുണ്ട്. Static case it is the solution of the Poisson equation. So Poisson equation is given by del square V is equal to minus rho by epsilon 0. Static case already said this is from the Maxwell's equation, del dot T equal to rho by epsilon 0, and E here is nothing but the negative gradient of potential. Taking negative to the right side, we have del dot del. Del dot del is nothing but the Laplacian operator, del square V is equal to rho by epsilon 0. So this is nothing but the Poisson equation. So negative is here, and you have studied the solution of this one. V is equal to 1 by 4 pi epsilon 0 integral rho d tau by r. So this is the differential form of the Poisson equation, and this is the corresponding solution or the integral form. So here V is the unknown function. So here the value of V is solved, and therefore it is the solution. So similarly, we know that B equal to del cross A. So in the magnetostatic case, we know that del cross B is mu 0 J. And substituting A over here, del cross A is equal to mu 0 J. So curl of a vector is gradient of divergence of that vector minus del square A equal to mu 0 J. ഇവിടെ നമ്മൾ del dot A എന്ന് പറയുന്നത് ചൂസ് ചെയ്യാനുള്ള ഒരു ഓപ്ഷൻ ഉണ്ടായിരുന്നു. The vector potential and scalar potential are not unique. നമ്മൾ ഡിസ്കസ് ചെയ്യും. And we have a freedom to choose the divergence of A. Curl of A ആണ് B വരുന്നത്. So we have a freedom to choose the divergence. So this is called the gauge invariance. And if we choose del dot A equal to 0, it is called Coulomb's gauge. So applying Coulomb's gauge over here, we will get del square A equal to minus mu 0 J. So this equation is similar to this Poisson equation, and therefore it is called the Poisson equation in magnetostatics. And we have the solution of this equation is equal to A is equal to. So instead of 1 over epsilon 0 here, we have mu. So mu 0 by 4 pi integral J d tau by R. So this is the expression for scalar potential and vector potential in the static case for electrostatics and magnetostatics. So these equations are obtained under static conditions, and they are the solutions of the corresponding Poisson equations. So this is the Poisson equation in magnetostatics, and this one is the Poisson equation in the electrostatics. So this solution A equal to mu 0 by 4 pi integral J d tau by R, and V equal to 1 over 4 pi epsilon 0 integral rho d tau by R may be time dependent if J and rho are time dependent. But these equations neglect the time retardation effects due to the propagation of the electromagnetic waves. Electromagnetic waves ഒരു particular velocity propagate ചെയ്യുന്ന അതിന്റെ time retardation effects ഈ രണ്ട് equations neglect ചെയ്യുന്നുണ്ട്. പക്ഷെ ഇത് എല്ലാ കേസിലും നമുക്ക് നെഗ്ലക്ട് ചെയ്യാൻ പറ്റില്ല. So this can be neglected if rho and J vary slowly with time. So that means the frequency of variation of rho and J is very, very small. So rho and J vary with a very, very small frequency. So frequency small means the corresponding wavelength is very, very large. ഒരു പെർട്ടിക്കുലർ വേരിയേഷൻ നമ്മൾ എടുക്കുകയാണെങ്കിൽ the wavelength is very, very large. വലിയ വേവ് ലെങ്ത് ആയിരിക്കും വരുന്നുണ്ടാവുക. സോ ഫോർ എ പെർട്ടിക്കുലർ ഇന്റർവെൽ R, if R is very, very small compared to the wavelength, അങ്ങനെ നോക്കുകയാണെങ്കിൽ rho ഏകദേശം ഒരു കോൺസ്റ്റന്റ് ആണ്. Rho is a constant and J is also a constant. So we can use this equation in that case only. So when the frequency of variation of rho and J is very small and therefore the wavelength is very large compared to the range of interest R here, we can neglect the time retardation effects and we can use these two equations. So such cases are called quasi-static. So since it is not static, we cannot say it is static alone. It is quasi-static, that means semi-static. So time varying ആണ്, ബട്ട് അത് സ്റ്റാറ്റിക് പോലെ സ്റ്റാറ്റിക് ഇക്വേഷൻസ് ഒബേ ചെയ്യുന്നു. അപ്പം നമ്മൾ ആ റേഞ്ചിൽ നമ്മൾ അത് ഏകദേശം സ്റ്റാറ്റിക് ആയിട്ട് കൺസിഡർ ചെയ്യാം. സോ ഇറ്റ് ഇസ് ക്വാസി സ്റ്റാറ്റിക്, static but not so static. But if the frequency is very high, wavelength is very small and R will not be less than lambda, and we cannot use those equations to get the scalar and vector potential. So these equations can be used only for static or quasi-static cases. So the quasi-static field approximation is true only for low frequency case. So if the source frequency is high, we cannot use this approximation, and we cannot use the Poisson equation also. So we have to get the wave equation for time varying case, for high frequency case, and we have to get the corresponding solutions. So the corresponding values for rho and j. So for that we are going to get the wave equation for the time varying case. So for that we use the Maxwell equation. Del cross H is equal to J plus dou d by dou t. So here H is B by mu. So del cross B by mu is equal to J plus D is epsilon E. And H is B by mu. So substituting it over here, dou epsilon E by dou T. So taking epsilon outside, we have a J plus epsilon dou E by dou T. So now taking mu towards right, we have del cross B is equal to mu J plus mu epsilon dou E by dou T. So in this equation, we have to write the magnetic field and electric field in terms of the corresponding potentials. So B equal to del cross A, and V is equal to minus del V minus dou A by dou T. So we will get B is del cross A. Del cross A is equal to mu J plus mu epsilon dou by dou T of minus del V minus dou A by dou T. So this is curl of a vector. So we know the identity. Curl of a vector is the gradient of the divergence of that vector minus del square A. So this is the expansion for curl of A. So grad divergence of A minus del square A is equal to mu J plus mu epsilon dou by dou T of minus del V and minus dou square A by dou T square. Dou by dou T of dou A by dou T is dou square A by dou T square. So here mu epsilon is a common factor. So here we have a gradient operator here and a derivative operator here. So they are independent, and therefore we can interchange the position. So we can write the gradient operator first. So we have minus mu epsilon gradient of dou V by dou T. But mu epsilon is a constant and its position can be anywhere, and therefore we can write this term as all other terms will not change, minus gradient of mu epsilon dou V by dou T. And the last term is minus mu epsilon dou square A by dou T square. The common factor we apply. So we have a gradient operator and we can combine them together, and gradient of del dot A minus gradient of this. Right left plus mu epsilon dou V by dou T minus del square A. The right side plus mu epsilon dou square A by dou T square is equal to mu J. So now we can apply the Lorentz gauge or Lorentz condition here. Lorentz gauge. Degree gauge Lorentz gauge or Lorentz condition. അതായത് നമുക്കറിയാം D എന്ന് പറയുന്നത് del cross A ആണ് അല്ലേ? അപ്പോ ഇനി നമ്മള് എയിലേക്ക് നമ്മളൊരു ക്വാണ്ടിറ്റി ആഡ് ചെയ്യണം, A prime, such that del cross A prime is equal to 0. അതായത് ഒരു ഇറൊട്ടേഷണൽ ആയിട്ടുള്ള ഒരു എ പ്രൈം ഇതിലേക്ക് ആഡ് ചെയ്യാണ്. അപ്പൊ ഇനീഷ്യലി എക്ക് കറസ്പോണ്ടിങ് ആയിട്ടുള്ള മാഗ്നറ്റിക് ഫീൽഡ് ബി ആണ്. ഇനി എ പ്ലസ് എ പ്രൈമിന് കറസ്പോണ്ടിങ് ആയിട്ടുള്ള മാഗ്നറ്റിക് ഫീൽഡ് നോക്കാം. ബി ന്യൂ is equal to del cross a plus a prime, so which is del cross a plus del cross a prime. So del cross a prime is 0 ആണ്. So this is del cross a alone. Del cross എന്ന് പറഞ്ഞാൽ നമ്മൾ b കിട്ടും. So b is a constant. So even though we change a from a plus a prime such that the curl of a prime is equal to 0, then the magnetic field does not change. So ഇങ്ങനെ infinite number of a primes possible ആണ്. നമുക്കറിയാം ഒരു ക്വാണ്ടിറ്റിയുടെ കേൾ 0 എന്ന് വെച്ചാൽ അതൊരു ഗ്രേഡിയന്റ് ഓഫ് എ സ്കേലാർ ആയിട്ട് എഴുതാൻ പറ്റും. സോ a is gradient of lambda. Lambda is a scalar function. A here is a vector function. Gradient സ്കേലാറിൽ ആക്ട് ചെയ്തിട്ട് വെക്ടർ കിട്ടും. സോ അങ്ങനെ ഇൻഫിനിറ്റ് നമ്പർ ഓഫ് സ്കേലാർ ഫംഗ്ഷൻസ് ഉണ്ട്. അതിനൊക്കെ കറസ്പോണ്ടിങ് ആയിട്ട് എ പ്രൈംസ് ഉണ്ട്. അപ്പൊ അങ്ങനെയുള്ള എ പ്രൈംസ് എല്ലാം എ കൊണ്ട് എയിലേക്ക് ആഡ് ചെയ്ത് കഴിഞ്ഞാൽ ദി ഫീൽഡ് ഡസ് നോട്ട് ചേഞ്ച്. ദാറ്റ് ഇസ് ഫീൽഡ് ഇസ് യുണീക്, ബട്ട് ദി പൊട്ടൻഷ്യൽ ഇസ് നോട്ട് യുണീക്. വി ക്യാൻ ഹാവ് എ സെറ്റ് ഓഫ് പൊട്ടൻഷ്യൽസ് എ പ്ലസ് എ പ്രൈം, എ പ്ലസ് 2a prime, a plus a double prime, such that the curl of a double prime is 0. അതായത് a double prime എന്ന് പറഞ്ഞാൽ gradient of other scalar quantity. അപ്പൊ അങ്ങനെയുള്ള infinite number of values for a are possible for a single value of b. So b is unique, a is not unique. So we have a freedom to choose the divergence of a. Curl of a fixed ആണ്, curl of a എന്ന് പറയുന്നത് b ആണ്. So divergence of a fixed അല്ല. Divergence of del dot a ആയിരിക്കില്ല del dot a plus gradient of lambda. But curl of a plus gradient of lambda എന്ന് പറയുന്നത് curl of a തന്നെയാണ്, b തന്നെയാണ്. കാരണം curl of gradient 0 ആണെന്ന് നമുക്കറിയാം. So the divergence is different for a. Del dot a not equal to del dot a plus gradient of lambda. So ഈ a plus gradient of lambda എന്ന് പറയുന്നത് നമ്മുടെ വേറൊരു സെറ്റ് a ആണ്. നമുക്ക് അതിനെ a1 എന്ന് വിളിക്കാം. So del dot a not equal to del dot a1. ഈ del dot a1 ന്റെ വാല്യൂ എന്ന് പറയുന്നത് del dot a plus del square lambda. So for infinite number of values of lambda, we have infinite number of divergence of the vector potential are possible. So our vector potential is not unique, but its curl is unique, but its divergence is not unique. So we have an infinite set of values. So we have a freedom to choose the divergence of a. So if we choose the divergence of a equal to 0, it is called Coulomb gauge or Coulomb condition. Coulomb's gauge. ഇതാണ് നമ്മൾ ഡിസ്കസ് ചെയ്തത്. അതായത് Poisson equation for J. ആ കേസിൽ നമ്മൾ Coulomb's gauge ഡിസ്കസ് ചെയ്തിട്ടുണ്ട്. So and we can also choose del dot A equal to minus mu epsilon dou square A by dou T square. എത്രയും വാല്യൂസ് എ പോസിബിൾ ആയതുകൊണ്ട് നമുക്ക് പല രീതിയിൽ അതിനെ ചൂസ് ചെയ്യാം. ഇഫ് വി ചൂസ് del dot A as minus mu epsilon dou square A by dou T square, it is called Lorentz gauge or Lorentz condition. So in Lorentz gauge, del dot A plus mu epsilon dou square A by dou T square is equal to 0. So applying this Lorentz gauge in our equation, we will get this quantity 0. So gradient of 0 equal to 0, and we have the equation reduced to minus del square A plus mu epsilon dou square A by dou T square is equal to mu J. So multiplying by negative sign, we have del square A minus mu epsilon dou square A by dou T square is equal to minus mu J. So we got an equation for A only. Initially we had an equation depending on both A and V. So what Lorentz gauge has done is to decouple the equation. So initially the equation was coupled. It contains both V and A. So applying the Lorentz gauge, we got an equation for A alone. And this one called the non-homogeneous wave equation for vector potential. It is called a wave equation because its solution represents waves traveling with a velocity equal to 1 by root of mu epsilon. So this is of the form del square A minus 1 by V square dou square A by dou T square is equal to minus mu J, where the velocity of the wave is 1 by root of mu epsilon. So we have used Lorentz gauge to decouple the equation. We can see that under static conditions, the Lorentz gauge reduces to the Coulomb's gauge, del dot A equal to 0. This term, time dependent term, will be 0. Since A is a constant in time, dou A by dou T is 0 and dou square A by dou T square equal to 0. We can get the corresponding equation for the scalar potential using the equation del dot D is equal to rho. So D is equal to epsilon E, del dot epsilon E is equal to rho, and del dot E is equal to rho by epsilon. And we know that electric field in terms of potentials is minus del V minus dou A by dou T. So equal to rho by epsilon. So we have del dot minus del V. So this is minus can be taken out. Del dot del is del square, the Laplacian operator, minus del dot dou A by dou T is equal to rho by epsilon. So here we interchange with respect to time operator and the position with respect to operator. So dou by dou T of del dot A equal to rho by epsilon. So here this is a coupled equation in A and B. So we can also decouple it using the Lorentz gauge. Del dot A equal to minus mu epsilon dou V by dou T. That is our Lorentz gauge condition. We already know Lorentz gauge. So applying it over here, we will get minus del square V minus dou by dou T of del dot A minus mu epsilon dou V by dou T is equal to rho by epsilon. So now we have minus del square V, minus minus plus here, mu epsilon can be taken out, plus mu epsilon dou square V by dou T square is equal to rho by epsilon. So multiplying by negative sign, del square V minus mu epsilon dou square V by dou T square is equal to minus rho by epsilon. So this is the non-homogeneous wave equation for scalar potential. Non-homogeneous wave equation. So this is a wave equation because its solution represents waves moving with a velocity 1 by root of mu epsilon. So we got the non-homogeneous wave equation for the vector potential and scalar potential. In both cases, we could see that the Lorentz gauge condition decouples the wave equation for the scalar potential as well as the vector potential. So initially it was a function of both A and V. So here we got an equation for V alone. So under static case, this term is equal to 0, del square V is equal to minus rho by epsilon. That's a Poisson equation. And under static case, this becomes del square A equal to minus mu J, the Poisson equation for magnetostatics. And we have seen that these are the solutions of the Poisson equations, and this cannot be the solutions of the non-homogeneous wave equation for scalar and vector potential. So we have to modify this equation for time varying case to get the solution for non-homogeneous wave equation for scalar and vector potentials. Okay, thank you.